Hi, Dr. Pingle here with a second part of the lecture on terrain models. This is part 2, DEM derived products. So the DEM is in our usage here, we're going to call it the raster of elevation. So we've got a grid of elevation values. And oftentimes we might visualize that. So in the previous lecture, we talked quite a bit about different visualizations for elevation data, including most particularly the shaded relief or hill shaded map. However, there are a number of different products that you can generate as well. So these are useful for all kinds of different analyses related to terrain. So this is as opposed to sort of just visualizing. These are going to be used for analysis functions. So the first of these is aspect. So this is just simply the direction that a slope faces. We can calculate slope. So what is the sort of maximum slope for that grid cell? And we're looking at the angle from horizon, either in degrees or in percent slope. We can calculate the curvature, which is whether that landform bends up or down. Think about ridges or valleys, whether it's concave or convex. We can generate contour lines. So a topographic map is usually going to have contour lines on it. We can take a DEM and we can actually generate those directly from the raster, and vice versa. And then we can generate a viewshed. So this is maybe a bit new. This is simply an area that is visible from a certain point on the raster. So imagine if you put if you were standing on the side of a hill slope, what could you see? Or if you put up a tower, or maybe you put in, let's say, a military installation that you wanted to make sure you could see things, the viewshed analysis would tell you what you could see from a given viewpoint. And then finally, you can create a tin. So this is a triangular polygon, or a lot of triangular polygons representing the land surface. So the first of these aspect is maybe one of the easiest. So this is just going to, using kind of the local neighborhood, it's going to calculate sort of what area, what direction that land faces. The tool itself is quite easy. There aren't very many inputs or outputs. You really just have to specify the input raster and the output. And it's going to generate a number of different values for you. So these values are going to be numerical values between 0 and 360, but also -1 for any place that's read as flat. What you see down here is a visualization of that data. So it's color-coded by bin. So north is anything between 0 and 22.5. But also notice at the bottom anywhere between 337.5 and 360. So anything that's kind of generally north. We've broken these up into sort of the eight main directions, so north, northeast, east, and so on. The visualization, the color visualization for this isn't outstanding. It's common, but it's pretty easy to figure out what is what. So you can tell what faces what direction just based on the color. But do keep in mind that the actual numerical value is encoded in the raster and that you're just looking at a visualization of it. One of the most common derived metrics for a DEM is slope. So this comes in handy for a variety of different reasons. If you're building a road or if you're building a house, you might need to do a slope analysis to figure out what the maximum slope is, the average slope, how much material you're going to need to move. Many kinds of construction projects are going to avoid building anything where the slopes are too high. On the other hand, if you're trying to build a ski slope or a ski site, you may be interested in finding places where the slopes are steep. So slope analysis does come in handy pretty often. The inputs for this are going to be sort of what you would expect. So you're going to need a DEM. You're also going to need to specify whether you want the output in degrees. So 0 all the way up to 90 degrees, or percent slope, which is rise over run. So this is one that causes people trouble sometimes. Those two are not interchangeable. If you think about it, a 45-degree slope is actually a 100% slope. So on a 45-degree slope, every 10 feet I go out, I go 10 feet up. That's 10 over 10, or 1. That's 100%. So maybe if you don't quite get that, maybe review some of those concepts. It's the same kind of thing that you would have learned in trig or in geometry. So just kind of review that. Those two numbers are quite different, and sometimes you'll run into GIS projects where they're specifying a maximum of 10-degree slope, or they might specify a 10% slope. And again, those are very different numbers, so be sure you know what you're working with. The last thing that you're going to need is a z-factor. So remember that DEM is often going to be distributed in some kind of a latitude and longitude based system, a degree based system, whether it's 1 arcsecond or a 3rd arcsecond. And so the vertical units are often either in meters or feet, more often meters. But in any case, you're going to need to define the ratio of the horizontal unit or the degree to the vertical unit or meters. You can look these up on a table. This was discussed in the last lecture. So if you're interested in more detail on that, I will refer you back to that. The way slope is actually calculated is worthwhile to take a quick look at. I'm not expecting you to memorize this, but it is important to know that what we're looking for is the maximum aerial slope between a pixel and its 8 neighbors. So there's a formula that goes into figuring this out. That formula is listed here. Essentially what we're doing is we're looking to calculate sort of the direction in the vertical direction, the slope in the vertical direction, the slope in the horizontal direction, and applying some weights to that to figure out exactly what that maximum slope is. So think of that as the uphill slope. This is an example of what that would look like. Don't worry about the outer pixels here, but if we have a neighborhood of 3 by 3 and the center pixel has a height of 30, let's say meters, the cell size is 5 units, we could calculate the slope based on that. So if you think about going between, if we look at this horizontally, right, if we're moving from left to right through that middle pixel, the slope is 0, right? You go from 30 to 30 to 30, so that's flat. But if you're moving northward from 10 to 30 to 45, that's actually quite steep. So we moved, if the pixel size is 5 meters, if I move from the 10 to the 30, I've gone up 20 meters when I've only moved horizontally 5 meters. So that's quite steep. That's way above 45, and in fact that's 75 degrees. Maybe not that one precisely, but the overall average of the steepness from 10 to 30 to 45, according to the formula in the last slide, will give you a slope value of 75. So that's quite steep. It's worthwhile to sort of maybe work through this example, and I provided a link for how slope works, produced by Esri. It's a little bit of knowledge here goes a long way. So see if you can sort of figure out why that center cell has a slope of 75 based on the numbers that you've got here. Once in a while, you'll see slope and aspect combined. So these are pretty nice visualizations. They're kind of pretty. They kind of, it's early attempts in cartography at multivariate mapping with rasters. So this came out in 1991, collaboration of Mollering and Kimmerling producing this. And there are a couple of different variations of this, but essentially we're using color information to encode aspect and the saturation level to indicate steepness of the slope. So the brighter the color, the steeper it is. The more washed out the color, the flatter it is. So that sort of makes sense because the only time we really care about aspect is when the slope is reasonably steep. One of the other main products for DEMs is curvature. So this is really important because it helps us isolate things like ridges and valleys, which are very different. So it isn't necessarily the slope of those that we care about, but whether the land bends up or down. So this is an example of what the curvature toolkit looks like. Like many of these other DEM products, it's going to need a z-factor to calculate things accurately. There's also an ability to write out a profile and plan curvature raster, and we'll talk about those in a second. So this is just drawing your attention to that again. So there's plan and profile curvature. I think it helps to view these graphically. So profile curvature is going to be as we're moving down slope, we want to know, does the slope increase or does it decrease? In other words, does the landform bend outward or does it bend inward? A second kind of curvature, though, is planiform curvature, and this would tell you whether the moving across the slope or along the perpendicular to the slope, does the land bend outward or inward? So both of those two combined are usually used to demonstrate curvature as a whole, but very often in a GIS project, only one of these matters. So for instance, if you're trying to isolate ridges and valleys, what you care about is profile curvature, and you don't really care about planiform curvature. On the other hand, planiform curvature can be very useful in sort of enhancing some of the hillshades that we saw in the last lecture. This is an example of what the outputs of those look like. So again, plan curvature, very useful for identifying ridges and valleys. Profile is really sort of showing what's going on around. You sort of get this contour-like effect with this. The generating contour lines is also particularly useful. So DEMs have become the de facto standard for recording elevations. In the past, a topographic map, something like the USGS had, would be the main method for recording elevations. But now we use DEMs as our primary source. However, people are still very interested in taking a look at contours. They still find those useful in their topo maps or other visualizations. And we can generate contour lines with a tool. So you just input your DEM, and then you export your contours. You have to specify a contour interval. So what's the distance between the contour lines? So usually this would be something like 10 feet, but depending on your, or 10 meters potentially. But it really kind of depends on where you are and what your purposes are. So there's really no right answer for a contour interval, but you need to know kind of what you're looking for. You might also define a base contour, so what you want to start at, and you are certainly going to need to define a z factor. In this case, I have a z factor of 1, indicating that I have projected my data ahead of time. This is an example of what the output of that would look like. So the black lines are the output of the contour tool. You can see that what we've generated is a vector file of some kind, either a geodatabase or a shape file. And this data has been overlaid on top of a standard hillshade. One of the really cool analysis features that's available in a GIS is the ability to conduct a viewshed analysis. So at the kind of cross section, you can imagine this as lines of sight. So if we have a viewer, the question is, what can that viewer see from their position? And so we might need to define things like a viewer offset, which is how far are your eyes above the ground, because that matters quite a bit for what you can see. And you would just sort of be sketching what you can see. So you can see the sides of the slopes that are facing you, but you can't see the sides of the slopes that are away from you. So the idea is that the taller you are, the higher the offset, the more you're going to be able to see. So this whole kind of feature of a GIS is called visibility analysis or viewshed analysis. And this is kind of one of the primary usage of a DEM. Wide application for this. In an urban area, you might be interested in saying something like, well, if I built a house, a 3-story house, and I've got a very detailed model of my environment, maybe created with LiDAR, am I going to block my neighbor's view? Am I going to be able to see anything? Those are very useful. Archaeology, so you might have places, certain sites might have been chosen by people based on what they were able to survey. And similarly, military science. So if you're going to position a lookout, you would want to, or build a fort, you would want to position those things where they're likely to do the most good, where they're going to be able to see key areas. So viewshed analysis can help you answer those questions. The viewshed tool, like all of these, is going to take a DEM. And then you're going to need to specify where you are. So this is typically going to be a point layer. And you're going to need to specify things potentially like a z factor, which is common to all of these. Visibility is a very similar tool. So here's where you can input things like the height above ground level, different kinds of analysis, refractivity coefficients. So if you want to take into account atmospheric conditions, you can do that. So the visibility tool is quite powerful, and I would encourage you to try using this just to produce an output. Of all of these different optional tools, this observer offset is really key. Remember that there's a lot of error and a lot of noise in a DEM, and you want to be able to kind of control for that. And so, you know, if the ground surface bends upward 1 inch from your position, you don't want to consider that blocked. What you want to do is include this observer elevation and observer offset features to make sure that you're specifying how high you are so that those little irregularities don't throw off the calculations. So this is an example of a raster output from the visibility tool. So if the observer is standing at this peak, and I don't remember offhand what offset was used here, but if they were standing at this peak, we run the viewshed tool, so what can they see standing at that point? This is the output. So in green are marked places that the observer can see, and in red places where they cannot. So you'll notice that it's not, there's some quite a bit of sort of noise kind of in here. These might be local features, but remember that these tools aren't perfect. So analyses have been run based on these visibility tools, and while they do perform fairly well, it's a relatively straightforward calculation. There are always things that don't quite go right. And so, you know, I would not place 100% confidence in, you know, whether or not this small little speck can be seen or not seen. Sort of look at it in terms of general trends. Finally, one of the really helpful things that you can do with a DEM is you can break it up into a tin. So tin-based analysis was really big. Years ago, one of the reasons why tin-based analysis is useful is that it can essentially find places where there isn't much change and represent that much more efficiently than a raster, or at least that's the theory. And so the idea is rather than record elevation at every single grid point, let's figure out which grid points we need to use and which ones we don't, and just use the ones that we do. So, for instance, if you've got a giant flat plane, there's no reason to record grid points at every single one. We could represent that with just a couple of triangles. You can create these in ArcGIS. They tend to be most useful for visualization and simplification. And with the advent of sort of 3D modeling, tins have been featured kind of a resurgence because here again we're interested in efficiency. There are really only so many faces, so each triangle is called a face. There are really only so many faces that can be represented efficiently, and so tin-based algorithms have been useful in sort of simplifying the terrain and representing it cleanly. One of the issues with terrain representation is the idea of very, very sudden changes, and so if you imagine sort of a 90-degree slope like the side of a building, that's actually very difficult to represent on a DEM because any difference in values is going to have some horizontal component, and so it's actually impossible to generate a true 90-degree surface using just a raster. Tins can help solve that problem, and they tend to do it with the addition of what are called break lines. So break lines are polylines, just linear features that are added into your analysis, and what you have here are sort of requests to the tin construction algorithm to treat things as vertical, so if you're trying to enforce it very strictly, you would use what's called a hard break line to say that things are truly vertical. Or you can use a soft break line to request a little more detail at that place. It might be something that's particularly relevant to an analysis that you're doing or something that you want to visualize. But break lines are going to be used to, as part of the tin construction process, to better model these discontinuities. As an example, this is what that would look like. A tin generated from a raster might look something like the image at the left. But if we want to enforce those break line restrictions, that would look something like the right. And so you're getting a lot more detail off of these sort of square features and the roadways, really making a much better product in the end. So this is just a quick introduction to a number of the different products and pieces that you can make from a DEM. Slope and contour are very popular. View shed analysis is popular in certain circles. Tins are increasingly less popular. They still have their place, again, especially in 3D modeling, but they tend not to be used as much anymore as they used to. So I hope you'll get a chance to practice some of these. I hope you found some of this stuff interesting. Definitely let me know if you have any questions. But thanks for listening, and we'll catch you next time.